So I just discovered that somebody left a comment on a video of mine from 2 years ago, and it's never too late to respond, right? They said that I made a mistake in my thermodynamics calculating the final temperature video, so I wanted to address that today in a little response and show you why I'm not wrong, although the way that I wrote it may be a little confusing, so I wanted to address that.
So the most important thing here is that energy is conserved. In thermodynamics, this is a really important idea. That means that there is no energy gained, there is no energy added, there is no energy lost in this system. It's all contained, it's isolated. So that means that we have to end and start with the same amount of energy. And this is where people get in trouble with this kind of setup. So let's play this out. So let's say that we are using Q equals mc delta T, and we have a situation where something is losing temperature. Its temperature drops. So let's say that it has initial temperature of 30 degrees and a final temperature of 18 degrees. Let's say it has a mass of a half kilogram and a specific heat of 800 joules per kilogram degree Celsius. If we plug in to find Q here, we will find that once we plug all of our information in, that final minus initial will give us a negative value for our heat. We get negative 4,800 joules. That means that heat is lost, but a more accurate way of thinking about this, because energy is conserved, is that energy is being transferred to another thing. So let's take this problem and apply it to a second circumstance. So let's say that this is a piece of metal. So let's update our equation there. And let's say that this piece of metal was dropped into a bucket of water. And we want to know how much water was in the bucket. Water has a specific heat of 4,186 joules per kilogram degree Celsius. Let's say the water started at 10 degrees Celsius. The important thing here is that the final temperature of the water has to equal the final temperature of the metal because they reach equilibrium. So if we plug in our value of Q from the previous problem into this example, then we will get a negative mass, which is not a thing. You can't get a negative mass. So we have to figure out how to set this up in a better way. So there is a better way. The better way to set it up is to deal with this problem right here. We can't set Q final equal to Q initial. Because although it is true that the total energy in the system is not changing, what we care about is the interaction between our two types of material. So if that's the case, then we don't care so much about the beginning energy and the end energy. We care more about the energy lost and the energy gained, which do not equal each other. The energy gained is equal to negative the energy lost. The reason that is because the energy lost is going to give us a negative number. So if we want those to both be positive, we have to make it negative. So let's take this and apply it to an example problem. Let's say that we have a mass of metal that's 0.275 kilograms, and let's say it has a specific heat of 775. It's initially at 46.3 degrees Celsius, and we have it drop it in a bucket of water with 2.76 kilograms of water, which is initially at 11.3 degrees Celsius. Remember that heat transfers from hot to cold, so since the water is colder than the metal is losing energy. So our total energy in our system has to equal the energy lost plus the energy gained. And so that has to equal 0, which means that Q water equals negative Q metal. Remember, Q metal is going to give us a negative number, so those two negatives will cancel. It's really important to remember that, otherwise you will get the wrong answer. So if we take this idea and we apply it with Q equals mc delta T, we can set mc delta T equal to mc delta T. And we can replace delta T with T final minus T initial. So if we take that and we multiply our T's out, then we get a big old mess of math that's just going to get worse because we need to solve this for T final. So now if we take both of our T final terms and put them on the same side by adding and subtracting terms from one side to the other, then we get an equation that gives us T final terms on the left and our T initial terms on the right. And if we factor the T final out on the left side term and divide, then we end up with an equation that solves for T final, which is going to be the mass of the metal times the specific heat of the metal times the initial temperature of the metal plus the mass of the water times the specific heat of the water times the initial temperature of the water divided by mW times Cw plus mm times Cm. And that gives us an equation for the final temperature of the water. So if we plug in our numbers to that, it's going to give us a value for the final temperature of this system. And now, one of the things that we're going to do here is we're going to check our work and make sure that we get a reasonable number. So 11.9 degrees Celsius is the answer. And if we think about what our initial values are, that has to make sense. The metal was at a really high temperature comparatively, 46.3 degrees Celsius. And the water was just a little bit colder than our final temperature, 11.3 degrees Celsius. Remember, water has a specific heat of over 4,000. This metal does not. So our temperature should be closer to the material that has a higher specific heat and more material. So when you're looking at your MC delta T math, please make sure that you ask yourself if the numbers make sense. That's the best thing that you can do for yourself here.
Okay, so I hope that clears it up. Remember that energy is conserved, and so in a closed thermodynamic system, the energy change has to be equal to zero. So whatever the metal gives up, the water has to gain. And the way that we write our equation at the beginning is really critical to getting the right answer. So I hope this provides some clarification, and I hope this helps you in whatever class you're working on when you click on this video. If you have any questions, feel free to put them in the comments, and I'll do my best to respond in shorter than 2 years next time. And I hope you have a good rest of the day. Thanks for watching.